Lecture 8.3, the magnetic force and its magnitude. A magnet produces a magnetic force on a moving charge. But we know more about how forces with fields behave. That is, a moving charge produces its own magnetic field. So there is an interaction between the magnet's field with the moving charge's field. In other words, that tells me that I have two interacting magnetic fields. So even though we're talking about forces, in the end, we have to talk about the fields interacting. The magnetic force depends on four physical parameters. It has to depend on the charge. It has to depend on the magnetic field, right? Or maybe the field strength. And because it's moving, it's got to depend on the velocity. So in other words, it's got to depend on not only the speed, but it has to depend on the direction. So we have to hit these. And we want to draw pictures with each of these four parameters all the time. So the first parameter we're going to go after is we're going to go after the electric charge. So what do I imagine here? I have a magnetic field that's present, and a charge is going to move through that magnetic field. So there's an external magnetic field, and then there's the magnetic field produced by the charge. Those two interact. So what we should think about then is that we have something like this. I have an external magnetic field. So let's say that this is my magnetic field right here. And I'm going to have the exact same magnetic field. I'm not going to change this magnetic field. So this is the magnetic field that's external to the charge. Now I have a charge. My charge is going to look something like this. So I'm going to say that because it depends on velocity, I'm not going to look at the details of the velocity. We're here to only do one thing. Look at the charge. So if I have one charge here, and over here, this guy has 4 charges. We clearly have a smaller charge here, and this is a larger charge there. So if the external field is fixed and the charges are different, the only thing that can matter now is that we have to worry about the velocity. We're going to assume that we do not change the velocity. So what we're going to find in this picture is this. If I have a larger charge, will experience a larger magnetic force. However, if I have a smaller charge, it's going to experience a smaller magnetic force. In other words, even though I don't know the direction of it, we're just looking at the magnitude. Because this is a smaller charge, it's going to have a smaller field. Because this is a bigger field, a bigger charge, it's going to have a larger magnetic force. So let's go look at the next thing. The other thing that it has to depend on is field strength. So now I have field strength. And this field strength is of course, the magnetic field strength. So what do I expect? If I have a stronger field, then it has to do with the line density. So in other words, we could say that if I have a line density that looks higher, I got to have a stronger field. If I have a lower line density, I got to have a weaker field. So then I'm going to compare my pictures again. So let's say that I have a field that's this strong. So in this case, that magnetic field is going to be small. On the other hand, I'm going to have a field that's going to look like this. And you could see here that this has a higher line density, so this has to be a bigger field. In other words, this is a weak field. This is a strong field, just like electric fields. So then I have to keep everything else the same. So if I have a charge here, I have to have the exact same charge here so that I only focus on the magnetic field. So each of these charges are the same, and I'm going to have the same velocity as I move into the field. So this charge is the same, that charge is the same. So then I have to be able to say that if I have a higher line density, that implies that I have a stronger magnetic field. But clearly, if I have a stronger magnetic field, it has to cause a larger magnetic force. Then, of course, the opposite happens. If I have a lower line density, I'm going to have a weaker magnetic field, and therefore I'm going to have a smaller magnetic force. So when I go and I draw here, I'm going to have a smaller force, and then here I'm going to have a larger force. I have to keep considering all of these components. Now we're getting to the velocity. It makes most sense to think of the velocity in terms of speed and direction and not mix them up. So then we're at the next piece. So remember, I'm breaking up velocity. So then we have to talk about the speed. So if I take the same situation as over here, so how about if we start to manipulate things a little bit now? So I'm going to say that I have a field like this. I don't care about weakness anymore. And then I have the exact same field. So what I'm keeping here is that I'm keeping constant the magnetic field. I'm keeping the electric field constant. So the one thing I'm changing is the speed. So if I come over here and I'm going to say, let me see if I can copy this for later. So now, if I see this, what happens if I have a higher speed? Well, since the magnetic field is produced by a moving charge, a faster moving charge should produce a stronger magnetic field. So then we go along the same thing here. We then say this, if I have a faster moving charge, then I'm going to produce a stronger magnetic field. And as a consequence, I'm going to get a larger magnetic force. But if I'm moving slower, then I'm going to produce a weaker electromagnetic field and therefore a smaller. That means here that now we could pencil in the size of the field. So this guy has to be smaller because this is moving. It has to produce a bigger magnetic force. Now let's get the direction of the velocity. So now we're at the direction. And the direction we'll define as theta. So this one's a bit odd. And the reason why this is odd is it's really a residue of the cross product. So I have this from last time. So now that I have a copy of this, I want to manipulate this guy right here. So what do I know? I don't care about the velocity. I only care about what the charges are doing. And according to the directions, it goes like this. The cross product says that if I have a velocity that's perpendicular, and we got to be specific when we say perpendicular, it's 90 degrees to the magnetic field. Then the other possibility here is that I can have a velocity that's parallel to the field. Now, we got to be careful when we say parallel because it really means parallel and anti-parallel. In other words, I can also have a charge. Okay, so if I take this and I move it over here, I can also have a charge that's moving against the field. It turns out that the cross product says this, that if we have a perpendicular field, or excuse me, a perpendicular component, a perpendicular velocity component, and that has a very specific meaning, which it's 90 degrees relative to the magnetic field direction, that tells us that it will experience a magnetic force. If you have a parallel slash anti-parallel velocity component, and that means either 0 or 180 degrees relative to B, then there is no magnetic force. In other words, the magnetic force here is not equal to 0. The magnetic force here is equal to 0. So in this situation, we literally have a magnetic force that's not 0. And here we have a magnetic force is 0. And that's by definition the cross product that actually gives you that. Now we've gone over the 4 things. And so now we can talk about the definition of the cross product. So definition. The magnetic force applied to a moving electric charge in an external magnetic field is given by FB vector, which is equal to QV cross B, where the magnitude of the electric force is then going to be QVB sine of theta, where that angle is given by this. So if I have a magnetic field in this direction, and it's most commonly defined relative to the magnetic field, it doesn't have to be that way. We don't have to do that. But that's what it's most commonly done, so that angle looks like this. So this is the magnetic force acting on a moving charge. Now, the only thing that's new here is the magnetic field, so we should talk about the units very briefly. So if I look at the units, one of the things that I'm going to see here is that unit-wise, the units of the magnetic field are new units. So that means if I look at a unit of force, then I'm going to have a unit of charge, a unit of velocity, and a unit of magnetic field. So if I manipulate this thing, a unit of magnetic field here is going to be a unit of force, which is a Newton, divided by a charge, which is coulombs, divided by velocity, which is meters per second. So what's common here is to take that second and combine it with the coulomb, and then this will then read an amp times meter into a Newton. And this, by definition, is 1 Tesla, which is typically written as just T. Now, a Tesla is a crazy number. This is a very large value. So if we're not dealing with large values, there's another one that's defined as a Gauss. So if we have, it turns out that 1 Tesla is equal to a different unit of magnetic field, which is called a Gauss. And this guy deals with small values for the magnetic field. Like, for example, the Earth's magnetic field is on the order of Gauss's. It's a, it's a fraction of a Tesla. Let's go interpret this now. So we want to look at the interpretation of the magnitude of the B force. So let's just look at just the very first thing is we want to look at, there's lots of details about the magnitude of the force, but what we really want to look at first here is we want to look at the magnitude of the cross product, which is related to the magnetic force. So we really are looking at the definition of a cross product. So here we go. The magnitude of the cross product is, as we've already defined, is equal to QVB sine of theta. There's nothing magical about this. It's just what it is. Where theta is the angle between QV and B. Now note, I included charge. Charge isn't a vector, but I'm going to include it. So if I start to look at this thing, what we're really looking at again is that we have our magnetic field, and then I'm going to say that this quantity here is the charge V, QV, where that's going to be our angle. So according to the cross product, the length of f of B is the area spanned by the vectors QV and B. Once again, the length of the magnetic field is the area spanned by these two vectors. That's the definition of a cross product area. So if I look at this, we want to look at this in terms of pictures. I almost feel like we should, maybe I should box this up just to make sure. Because it really is the important piece here. So now what we need to do is that we want to draw pictures to remind you what that means. So we need a reference. So when I think of a reference, I need to show what do I mean by them. So for right now, I'm going to assume that everything's in 90 degrees. So I'm going to have two vectors. I'm going to have a magnetic field vector. Let's say that this vector is 2 squares, and this is the magnetic field. And then I'm going to pick this vector here. And when I pick this vector, I'm imagining that I'm going to get something that then reads the charge times the velocity vector. Now, even though that angle does not look like it's 90 degrees, I'm going to say that it is. So if I look at the parallelogram rule, I'm going to get something like this. That spans a space, and this is the area spanned by these two guys here. So what I'm saying here is that this angle right here is 90 degrees, even though it doesn't look at that. So when I look at this area right here, that's the area of the cross product. And this guy is then going to be related to this magnetic field. That length is related to that area. So when I look at this thing, we say that f of b is then going to equal to q v b, but then I have sine of 90 degrees, which is of course 1. So when I'm writing this in the future, I'm always imagining that I have a 90-degree angle. Now I want to compare this. So how do I get a larger magnetic force? I could have a larger magnetic field. So if I have a longer magnetic field, so if that's 2 squares, you could see that I could draw this into being, let's say, how about not 4 squares? Let's say 3 squares. This guy is clearly longer. But if I keep my charge the same length, my charge times my velocity, so if Q and V are exactly the same, you could see here is that this area is going to be larger. And because this area is larger, I'm going to have a longer magnetic force. And I can repeat this process. What if I go faster? If I go faster, then I imagine that I have an area like this. And if I look at my magnetic field, I could say that if I go faster, then I increase the length of this guy, which then means, assuming that I have my regular magnetic field, I could then come in and look at this area. So if I look at this area, oops, that area is not long enough. You could see once again, I'm going to have a bigger area. Bigger area means larger magnetic force. And the other thing that we said that could cause a bigger magnetic force is a larger charge. I could come in here and I can extend this guy here now. So if I extend this guy to right here, I could say that my speed is small, but now my charge is large. So therefore, my magnetic force can be equally as large here as these other situations. So in other words, I can have the same area 3 different ways, and therefore like that. So in essence, if I look at the magnetic force here, I could say that this magnetic force is large compared to our reference because in this situation, we had little q v times a big magnetic field. in this situation, we had a little q, but a large speed. And then in this situation, we had a large charge while having a smaller speed and a smaller magnetic field. They all told me the same thing. So in summary, we could then say if I have a larger magnetic field, or I have a faster speed, or if I have a larger charge, this leads to a stronger magnetic force. And pictorially, that's exactly what it is. Now, another thing that we should think about is that because we are talking about velocity, we need to pay attention to the angle dependence. So I'm going to say, what about the angle dependence? So the angle dependence. So one of the things that we just learned here from the parallelogram rule, not the parallelogram rule, but the area of the parallelogram produced by the cross product, which spans those two vectors, is that the strength FB is equal to that area spanned. Depends also on the angle between QV and B. And we can break this down into three cases. So the first case that I'll consider is that what happens if I have parallel and anti-parallel QV and B. So picture-wise, we have to have the following thing. I have a magnetic field. Let's say that this is my magnetic field. And over here, I have a magnetic field. So if I have my velocity, I can have my velocity that's parallel, or I can have my velocity that's anti-parallel. But the cross product says that these guys don't span an area. So in this situation, we're seeing that at theta equal to 0 degrees, and at theta equal to 180 degrees, the area spanned is 0. So this says that the area spanned by QV and B is 0. And if it's 0, then that tells me that the magnetic force here has to be 0 as well. Because it has to do with that area spanned. So what this is really telling us is this. Any charge that moves parallel or anti-parallel to the magnetic field will experience no magnetic force. That's what that's telling us. So now we have two cases left. One, what happens if it's perpendicular? So I have perpendicular QV and B. So in this case, I'm going to have a top view. So if I have a top view of what's going on, you could imagine that I have a magnetic field that's going like this. And then I have my vector going like this, where this guy's going to be Q, V in that direction. So this is the area span. So you could see here is that if I start to look at this thing, this here represents the area. And you could see here is that this will then give you maximum area. But if it gives you maximum area, it has to give you maximum force. So then this tells us here is that picture-wise, if I now show what I mean by these vectors, I have a magnetic field that's then going to point here. And so if I now look at my vector here, we know that this vector here has to be given by this quantity right here. So if I look at this thing, this area then has to be maximum area. And when it has this maximum area between these two, in other words, I'm saying that this right here gives me an angle of 90 degrees, right? That's what that's telling me. It's a right angle. Then this magnetic force here will be maximum. So in other words, the magnetic force is maximum when I have Q, V, and B when this quantity is sine of 90 degrees. That's when I'm going to get maximum force. So now if I go to the last one, what happens if I have an arbitrary angle? That's spelled incorrectly. Where this angle is not 0 degrees, it's not 90 degrees, but it's in between. So if I look at this, then the area has to be smaller. Because if I look at the previous situation, now I have a magnetic field here, but now my area here, even if it's the same length, this area between these two vectors will not be the same. This will be a smaller area. This will be a smaller area. So what I'm saying here is that if I have an angle here, that's less than 90 degrees, then I'm going to get a smaller area, which then tells us that then I'm spanning a smaller area. So in other words, I'm going to have a field that's going to be something like this. And so if I compare those two fields, this area right here is smaller, right? And this is for an angle where theta is less than 90 degrees. So therefore, its force here will be smaller. In other words, it's non-maximal. Where again, I have Q, V, and of course, B in this direction. So what I'm seeing here, you know what, I should probably write this here. So then this FB here, when I write it out, this will then be Q, V, then I'm going to have B, and then I have a term here, which is sine of theta, and this quantity is smaller than 1. And that's what makes this guy not maximal. So picture-wise, I'm looking at these guys like this. So now what we're seeing here is that these angles let me not say angles, but angle dependent areas show that the velocity vector can be broken up into parallel and perpendicular components. In other words, we can write the velocity to be equal to v parallel, right? So this would be parallel, plus v perpendicular, and this will all be relative to the magnetic field. So when theta is equal to 0 degrees or 180 degrees, the parallel components of f of b vanish, while the sole survivor is the perpendicular component. So picture-wise, I imagine something like this. Remember, the field is always relative. Excuse me. these velocity components are always measured relative to the reference direction of the magnetic field. So you can imagine I have a magnetic field in this direction. So here's my B field. And I'm going to say that this is always going to be the reference direction. It doesn't have to be, but it's useful to pick that. So now I have velocity components. I have a velocity component that's going to be V parallel. I have another component that's going to be V perpendicular to the magnetic field. But you can see here is that this is really the velocity vector, which I'm just breaking down into its components. So now there's two components that I could think about. This guy has a magnetic field in this direction, right? There's going to be two magnetic fields. So when I look at the area spanned by these two vectors, you're seeing that this vector, V parallel, spans no area, whereas this guy gives you a spanned area. So in other words, here, we could say here is that there's no spanned area, which then tells you immediately that the magnetic force is zero. But here, we are spanning an area, right? This is telling us about the area right here. And it depends on that perpendicular component. So here, we do have a spanned area, which tells us then that the magnetic force is not zero in this situation. So if I write out the details of the magnetic force here, we could then say that the magnetic force in vector form should be QV cross the magnetic field will then be QV parallel cross B plus QV perpendicular cross B. You can clearly see that this term right here has to be zero because there's no area spanned. So the only surviving component has to be QV perpendicular cross B. In other words, the magnetic force in vector form should be QV perpendicular cross B. And this is the most common way to write it. Another way that you can write it in certain situations where we could look at the magnetic field perpendicular to the velocity. In some situations, that's more useful, but you also find that this is less common. So this is uncommon to actually see. So here is the actual form of the magnetic force and its direction. In other words, only perpendicular components have non-zero magnetic forces. One last thing that we want to look at is that we want to look at that magnetic forces do not change the speed of a charged particle. Magnetic forces do not change the speed of a charge. And that's the nature of a cross product. So let's see what we actually see here. There are two ways to accelerate a charge. By the way, it doesn't have to be a charge, but there's two ways to accelerate anything. One of them here is to accelerate anything, you can change its speed while maintaining constant direction. So in this case, that implies here that the force is either parallel or anti-parallel. To the velocity. So if I see the situation, so if I am going to speed up, the way I do this here is that I have a velocity that must be in the same direction as the force. That's what I mean by speeding up. Or if I slow down, I could then have my velocity still in the same direction, but now I have an imposing force in the opposite direction. That's what we mean by that. So in this situation, we then say that work is done to change the kinetic energy of a charge. However, magnetic forces are not parallel. However, magnetic forces only act perpendicular to the moving charge. So that means here that no work is done by a magnetic force. So in other words, charges cannot speed up if a magnetic force is doing the work. Speed up or slow down in magnetic fields. Which is kind of crazy when you think about it. There's a force, but it's not speeding up or slowing down the charge. So that brings us to our next situation here. You know what? I should box this because I think this is an important point. So if I have a constant speed while changing directions, that means here that the force is perpendicular to the velocity. So if I look at the situation, I could imagine that I have velocities that are going like this. I have a velocity that's coming like this. I have another velocity that's still going in the same direction, but now I have a magnetic force that's acting perpendicular, either in this direction or in that direction. What's going to happen? Let me spread these out a little bit more. What you're going to see here is that now this charge is then going to start to move. It's then going to circle around. It's going to circle in the counterclockwise direction. On the other hand, in this situation, it's going to move in the clockwise direction. In other words, it's going to start here, and then it's going to rotate clockwise. So in this situation, you could see that the force is not in the direction of the moving charge. So because the B force is not in the direction of the velocity, but perpendicular, it causes the charges to turn in circles and do not change the speed of the charge. Even though we've already said that, I think it's worth saying again. Because of this, magnetic forces only change, only change direction. And this is why sometimes they're called a deflection force. Not the speed.